Hey everyone, welcome back. Ever notice how predictable the world around us can be?
Yeah.
I mean, if you toss a ball up,
hmm
you can be pretty sure where it's going to land.
Right.
That's like classic physics in action, right?
Exactly.
The physics we see every single day.
It's a familiar world.
But what about when we zoom in? Like way in,
Uh-huh.
down to atoms and all those tiny particles.
Yeah.
Things get a little less predictable there.
A lot more interesting, too.
A lot more interesting, for sure.
Yeah.
So I guess classical physics, with all its laws about motion and gravity,
Mm.
works great for a lot of what we see.
It does. It's really the foundation for so many things. Engineering, architecture.
Right.
You think about it, even space travel.
It's pretty amazing.
All built on that.
It really is. But I know scientists started looking deeper.
Yeah.
And they found some spots where those laws, those classic laws, they didn't quite work.
Yeah, they didn't quite cut it anymore.
So let's talk about that. These like cornerstones of classical physics, what are they?
Right.
What makes them so reliable for like building bridges, launching rockets, all that stuff?
Well, one of the key things is this idea of determinism.
Determinism.
So if you know how a system starts, like the speed and position of that ball you tossed up,
Right.
classical physics says you can tell exactly where it's going to end up.
Okay.
It's all about cause and effect.
So no room for surprises.
Not in that sense, no.
All right. That makes sense. So it's like
Yeah,
a perfectly planned dance, everything moving predictably.
exactly. And along with determinism,
Well,
you have the idea of continuity.
Right.
In classical physics, things like energy or speed,
uh-huh.
they can have any value within a range.
Okay.
Think about a car accelerating.
Right.
It doesn't jump from 0 to 60 like that.
Yeah.
Smoothly goes through all the speeds in between.
Yeah, like a smooth curve.
Exactly, not a staircase.
Gotcha. So this classical approach, it's been successful, right?
Oh, yeah.
We've done some pretty amazing things with it.
It's given us a deep understanding of mechanics,
Okay.
how forces and motion all work together.
Right.
That's how we design, well, everything.
Yeah.
Cars, skyscrapers.
Makes sense.
And then there's thermodynamics.
Oh, yeah.
Explains how heat and energy work.
So engines and power plants.
Right, even your refrigerator.
Wow.
All based on classical physics.
It's really amazing to think how much of our world is built on these like basic principles.
Yeah, it really is.
But you mentioned earlier that there were these places
Yes.
where classical physics, it kind of broke down.
Yeah, as scientists started looking at the world of the very small, the realm of atoms and all those tiny particles, they ran into some real puzzles. Classical physics just couldn't explain what they were seeing.
So it's like the rules of the game, they suddenly changed when they got too close.
Exactly. Like one famous example, it's called blackbody radiation.
Blackbody radiation, huh?
So classical physics predicted that hot objects, like say a glowing piece of metal, should give off an infinite amount of energy.
At high frequency.
Right, at high frequencies.
Okay.
But when scientists actually measured it, it followed a very specific pattern.
Okay.
And there was just no way to explain that with classical physics.
So that sounds like a big problem.
It was a major problem.
Did they just throw out all of classical physics then?
No, not at all. It's still incredibly useful for describing the world on a large scale.
Right, right.
But that problem with blackbody radiation, along with some other things they were seeing, pointed to the need for a new physics. One that could explain things at the atomic level.
So this is where quantum mechanics comes in.
Exactly.
Yeah, I've heard it called the physics of the very small.
That's right.
But it's always sounded kind of intimidating to me.
I get that.
Yeah.
It can seem strange. Because it challenges how we think the world works. But at its heart, quantum mechanics is a more fundamental way of looking at reality.
Right.
It includes classical physics. But explains those things classical physics can't.
So classical physics is like a simplified version for everyday stuff.
Right, exactly.
But when we need to get down to the details,
Yeah.
we need quantum mechanics.
Exactly. Think of it this way.
Yeah.
You can use Newtonian physics, part of classical physics, to figure out the path of a ball, right?
Right.
Good approximation.
Yeah.
Works for most things.
Right.
But what if you need to be really precise,
Okay.
like calculating the path of a satellite?
Mm-hmm.
You need Einstein's theory of relativity,
Okay.
a more refined way of looking at it.
Gotcha. So it's all about the right tool for the job.
Exactly.
Okay, so one of the big ideas in quantum mechanics is that energy, unlike classical physics, isn't continuous.
Right. It comes in these little packets.
Packets.
Yeah.
Or quanta.
Quanta. Okay. And this idea of quantization helps explain those patterns in blackbody radiation.
Right.
Okay, it's like energy can only exist at specific values.
Like steps on a ladder.
Exactly. Not a smooth ramp, it's a staircase.
Gotcha. So how does quantization work with an electron in an atom?
Okay.
I always picture electrons like tiny planets.
All right, orbiting the nucleus.
Yeah, like a tiny solar system.
That's a common way to picture it.
Yeah.
But quantum mechanics says it's not quite right.
Yeah.
Electrons in an atom, they don't follow orbits like planets.
Okay.
Their energy is quantized.
Right.
So they can only exist at certain energy levels.
So they're restricted. They can't be just anywhere.
Yes. Think of it like floors in a building.
Okay.
They can't be between floors.
Right. Gotcha.
And when an electron moves between these energy levels, it either absorbs or releases a photon.
A photon, right?
A packet of light.
Okay.
With a specific energy, the difference between the levels.
Okay.
This is how we get things like emission and absorption spectra.
Right.
The fingerprints of different elements.
So it's all about jumps between energy levels.
Right.
Not smooth transitions.
Exactly.
This is really different from the classical picture.
It is. And quantization helps explain why atoms are stable.
Yeah.
In classical physics, that electron orbiting, it would be constantly losing energy.
Right.
Eventually spiraling into the nucleus.
So the atom would collapse.
Exactly. It would just collapse.
I'm glad our atoms are stable.
Yeah, me too.
That doesn't sound good.
But quantum mechanics,
Yeah.
because the electron's energy is quantized, it can't just lose energy and spiral, and it has to be in one of those energy levels.
Right.
And the lowest one is stable.
So it's like a safety net.
Yeah, a safety net.
Okay, that makes sense.
Keeping the atom from collapsing.
So if everything's quantized at the atomic level, why don't we see these effects in our everyday lives?
Right. Good question.
I mean, the world seems pretty continuous to me.
It does. And the answer is the quantum effects get less noticeable as we deal with bigger systems.
So bigger things, fewer quantum effects.
Think of it like the energy levels in an atom.
Okay.
They're very close together.
Right.
But as you get to larger objects with trillions of atoms, the space between the energy levels, it gets so tiny, it's basically continuous.
So it's like the little quantum steps.
Yeah.
They get smoothed out when we zoom out.
Exactly. Like looking at a digital image up close.
Right.
You can see the pixels, but zoom out.
And it looks smooth.
It all blends together.
Okay, I see how classical and quantum physics can fit together.
Yeah.
But earlier you said quantum mechanics challenges how we think the world works.
It does. One of the most mind-bending things.
What's that?
It's called wave-particle duality.
Okay.
It's the idea that light and even matter can be both wave and particle.
Wait, both? How is that possible?
It seems impossible.
Yeah, totally different things.
Right, but experiments have shown light can act like a wave.
Okay.
Like in diffraction and interference. And like a particle.
Like what?
Like in the photoelectric effect.
Okay.
And particles, like electrons.
Right.
They can even show wave-like stuff.
Oh, wow.
Like interference patterns.
Okay, so light and matter are both at the same time?
In a way, yes. It's not that they're switching.
Right.
It's more like our ideas of wave and particle aren't enough to describe them.
They don't fit.
They show parts of both.
Okay, that's wild. So does this mean that at the quantum level, things are unpredictable?
That leads us to another big idea.
Okay.
The uncertainty principle.
The uncertainty principle, okay.
It says there are limits.
Limits to what?
To how precisely we can know certain pairs of properties of a particle.
So like what kind of properties?
Well, one famous example is the uncertainty between position and momentum. The better we know the position, the less we know about its momentum, and vice versa.
So it's like trying to grab a cloud.
Exactly.
The harder you squeeze, the more it slips out.
And this isn't because our instruments are bad.
Okay.
It's just how nature is. At the quantum level, there's this fuzziness.
Fuzziness.
Yeah, an uncertainty we can't get rid of.
It's built in.
It really is.
So the quantum world is fundamentally different.
It really is, yeah.
From what we experience.
It is, but it's also full of wonder.
Yeah.
And as we explore it, we're making incredible discoveries.
That's great.
Pushing the boundaries of our understanding.
Okay, so we've talked about how quantum mechanics changed how we think about atoms.
Yeah.
But what about the bigger picture? Like, how does it affect our view of the whole universe?
Well, quantum mechanics really impacts cosmology.
Cosmology, right?
The study of how the universe began and evolved.
One of the biggest mysteries there is the Big Bang, Right. The idea that everything started as this super hot, dense point, and it's been expanding ever since.
Exactly. And classical physics.
Yeah.
It can describe that expansion from a pretty early point.
Right.
But it can't tell us about the very beginning.
Like the moment of the Big Bang itself.
Right. It hits a wall there.
Okay, so we need quantum mechanics.
We do, to understand those first fractions of a second.
Wow. So what does quantum mechanics say?
Well, it suggests that the universe might have come from a quantum fluctuation.
A quantum fluctuation. Okay.
A random event in what's sometimes called a quantum vacuum.
So the whole universe.
Yeah.
From a tiny quantum blip.
It's a leading theory.
That's wild.
And it might not be as crazy as it sounds.
Okay.
Remember, in quantum mechanics, things like energy particles, they can pop in and out of existence.
Because of the uncertainty principle?
Right. That fuzziness at the quantum level.
You're saying the universe might have popped into being.
It's a pretty mind-bending idea.
Yeah, it is.
But it fits with what we know about quantum mechanics.
So the universe, at its most basic level, is maybe way stranger than we thought.
It might be, but if quantum mechanics is so important, why don't we see more of its effects every day?
Right. Why does everything seem so predictable?
Well, that's because of something called decoherence.
Decoherence, huh? What's that?
It's the process where quantum systems, they lose those quantum properties.
Like superposition.
Right. Superposition, entanglement, when they interact with their environment.
So the quantum weirdness disappears.
In a way.
When things get bigger.
Yeah. Or more complex.
Okay.
In the tiny world, quantum effects are strong.
Right.
But as systems grow bigger, interact more with their surroundings, decoherence kicks in, and they start behaving more classically.
It's like a transition.
Yeah, a gradual one.
From the quantum to the classical.
Exactly, and that's why we don't see things like cats in superposition or objects teleporting.
Decoherence makes the world seem stable.
Yeah, more predictable.
So is quantum mechanics only about the very small then?
Not at all. It's led to so many technologies from lasers and transistors to medical imaging and GPS.
Okay, so it's not just a theory.
No, it's affecting our lives every day.
In practical ways.
Absolutely, like lasers. Used in everything from barcode scanners to fiber optics. They're based on stimulated emission.
Okay.
This quantum idea that photons, they can interact with atoms to make more photons.
So when I scan groceries, I'm seeing quantum mechanics.
In a way, yeah.
That's amazing. What about these quantum computers I hear about?
Those are really interesting.
Yeah.
They use superposition and entanglement to do calculations that normal computers just can't.
So they could revolutionize things.
They could. Fields like medicine, materials science, even AI.
What could they solve that regular computers can't?
Well, for example, drug discovery.
Okay.
They could simulate how molecules behave. Help design new drugs.
Wow.
With incredible precision.
That's amazing.
And material science, too.
Yeah.
New materials with crazy properties.
So quantum mechanics is opening up all these possibilities.
It really is.
It's incredible.
And as we keep exploring,
who
knows what else we'll find?
This has been an incredible journey.
It has.
Exploring the world from huge to tiny.
Right.
From those familiar laws of classical physics to the mind-bending world of quantum mechanics.
It really is mind-bending.
It seems like our understanding of the universe is always changing.
It is. There's always more to learn.
That's what makes science so exciting.
It really is.
This constant discovery, trying to understand the universe.
And our place in it.
I'm leaving this conversation with a sense of awe.
I hope so.
And a real appreciation for the complexity of it all.
It's pretty amazing.
Thank you so much for being here.
It's been my pleasure.
For sharing your expertise with us.
Happy to do it.
And guiding us through all of this.
It's been fun.
And to everyone listening.
Yeah.
Keep asking those questions.
Right.
Keep exploring. And never lose that sense of wonder.
The universe is full of mysteries.
It really is.
Waiting to be discovered.
I can't wait to see what's next.
Me too.